Okay, so we're just going to go over one-sided limits as we first start, followed up by, we'll do two-sided limits at a point. But let's go ahead and see where we're at here. So in the IXL practice, you guys saw a lot of graphing problems where they asked you what would the limit would be at that point when we're looking at a graph. Well, I'm going to do the same thing here, except I'm going to kind of edge you guys into not using a graph. And having a graph is great, but we're not always going to have a graph. And not having a graph doesn't mean we can't find the limit. So the first question is, we got to pay attention to the very particular parts of a limit, the way we're writing it. And I'm looking here as limit as x approaches -2. Now is -2 left or right? Think about it. Negatives are on the left side or right side of a graph? Left. So this is from the left side. So looking at the graph as we approach from left to right, or sorry, left or right, we're approaching from the left side going toward x is 2. And x is 2 is right here. As we start walking toward that wall, as we start walking toward 2, what's the y value? What is the f value? What is that y value? You know, so as we are walking toward my x is 2 from the left side, the y value starts to drop. And the left side looks like it's going to be 1. Okay, so we're saying the graph looks like 1. The answer is 1 here. Now, what will that look like in the equation form? So if I look at the equation here is given of both those graphs. The left side, look, x is less than 2, that's the left side, and x is greater than 2, greater is bigger, 3, 4, 5, 6. So that would be the right side. And as we look at the graphs, this is a line, which is a line equation. And look at x squared. X squared is not a line, it's a parabola, and since it's negative, it's facing downward. Okay, just to show that the graphs and the equations are the same thing. The equations are represented by the graphs. So my question is, if I was given not the graph and just given the equation, which of these two equations would represent 2 from the left side? Would this be considered the left side, or would this be considered the left side? X is less than 2, or x is greater than 2? X is less than 2, or x is greater than 2? Right? So we're asking these questions repeatedly so you guys can get into the mode of understanding, hey, this is just a nice way for mathematicians to say, look at the left side, which is just x is less than 2. So I'm going to choose this top equation because this is an equation that's less than 2. That's on the left side of 2. So what would the value be if I plugged in 2? Let's go and plug in 2. Here, x is 2. -2 times 2 plus 5, it's -4 plus 5 is 1. And remember, that's actually the same answer we said before, that the limit as x approaches 2 from the left side, it looks like 1. Look at the graph here, everyone. Look, zoom in, zoom in. That looks like 1 from the left side. Not only do we do that from the graph, when we plugged it in from the left side using the top equation because x is less than 2, we also got, when we plugged in the values for 2, we also got the answer 1. So these answers are the same. Okay. What if I change this question slightly, and instead of putting a negative sign, I went ahead and I made this into a plus. The limit, let me use a different color. Limit as x approaches 2 from the plus, the right side of x. Well, on the graph, this is the right side. As we get closer to 2, the y value starts crawling up, and the y value looks like it should be 0, right? Isn't that 0? Clean that up. The y value looks like 0 from the right side. Well, would that have been the same answer in the equation? Well, let's go ahead and look at the equation. The right side is using the bottom equation right here. The second equation, when x is greater than 2, the number is greater than 2 on the right side. If I plugged in, hey, what does it look like at 2? Let's go ahead and plug in 2 and plug in 2. That's -2 squared plus 4 times 2. Oops, times 4 times 2 minus 4. That's going to be -4 plus 8 minus 4. And as you can tell, that also is 0. So whether we look at the graph or plug it into the equation, they should give us the same exact answer. limits don't really get much harder than this. Like, as long as you know how to read the equation, read which limit we're going to use, and plug it into the equation, deciding if it's left or right, it's pretty much that easy. Looking at this one, we're being very specific. Number 2, x is approaching 3 from the left side, not negative 3, 3 from the left side. It's our math notation. So from the left side, we're looking at this graph here. That's the left. And as x approaches 3, that's 3 right here, the y value looks like it's getting closer to 8, 9, 10. That looks like it's going to be 9. When we verify this using the function, I'm seeing x is less than 3. That's my left side. X is greater than 3, 4, 5, 6. That's for the right side. I want specifically the left side. So we'll plug in x, 3, into the problem. So let's plug in 3 here. 3 times 2 is 6. 2, plug in 3, plus 3. It's 6 plus 3 is the 9 we wanted. Okay? So these equations at the top are just the formula version of the graph that's given. Of course, if they give us the graph, it's super nice. We can just look at the graph. But if we're not given the graph, we can always plug it into the equation. Okay? Our function versions of it. So we look at the problem as we continue. We have absolute value. That's always a little tricky. So my question here is, let's jump to a little hard. So what would the graph look like if I plugged in a negative 2 from the left side? Negative 2 from the left side. So if I just plugged in negative 2, if I plug in negative 2 here and plug in negative 2 here, we'll see something kind of funny happen. So negative 4 times negative 2 minus 8 over negative 2, negative of negative 2 minus 2, absolute value. This becomes positive 8 minus 8 over 2 minus 2, which is 0 over 0. And this is what we call indeterminate. And indeterminate means we were not able to determine it. Duh. We're not able to determine it. So we have to try another method. So that other method we're going to try is, we're going to go ahead and try factoring it. But we want to realize that absolute values aren't always positive. What I mean by that is that they eventually become positive, sure. So what happens to the top number? Since this was going to be 0 on top, it's actually balancing on the plus and minus. So if I was a little bit to the right, this would be positive, most likely, or negative. And if it was on the left, it would be negative. But let's go and see what would happen to this number. Well, let's actually go ahead and simplify the number first. If we say negative 4x minus 8 over negative x minus 2, or our second version is going to negative 4x minus 8 over negative x minus 2, or make this negative. Now, whenever you have absolute values, you want to come up with two versions. Why did I say two versions? Is because one of them could have been a negative and one of them could have been a positive. So let me give you an illustration of this. If I plug in a value here, that's a smaller than negative 2, like negative 1. Would this whole answer be positive or negative? Okay. But what if I plug in a number that's bigger than negative 2? Okay. Let's say if I plug in, bigger and smaller. What I mean is, again, number line, here's negative 2. If I plug in numbers over here, which are larger, numbers here are smaller. Negative 1, 0, and negative 2, no, negative 3, negative 4, negative 5, just so you can visually see that. Here's my negative 2. If I plug it in negative 2 here, we said this was going to become 0, right? That wasn't going to work for us. So what we're going to do, this is a trick when it comes to absolute values, is that we are going to make a decision. Do I give it a negative or no negative. So why do we do this? Let me go ahead and do a side illustration. What makes an absolute value an absolute value? So what makes an absolute value an absolute value? So if I say the absolute value of x is equal to 3, x could be 3, and x could be negative 3, right? So essentially, x is my answer, but I could have negative x depending on what value I want to plug in. If I plug in x is positive 3, hey, that's our answer. If I plug x is negative 3, hey, doesn't that force it to be positive? So you can always write an absolute value in two different versions to represent the same thing, except you have to say some conditions. When x is greater than 0, we're going to use this version here. When x is less than 0, we use this version here. So let's use that again. If I say the absolute value of x, and I give you these two versions, we're going to use let's say f of x. Okay, f of x can be rewritten as two different equations. We can call it x when x is greater than 0, and negative x when x is less than 0. If x is 3, does that fall in the top equation or bottom equation? If x is 3, top equation or bottom equation? If x is positive 3, we would use the positive equation. Hey, if we just plug in 3, isn't that the same thing as just absolute value of 3 is 3? Same answer. What if I say x is 5? Absolute value of 5 is 5. Same answer. What if I put x is, let's use a negative one. Where would negative 3 fall? The top equation or the bottom equation? Negative 3. Negative 3 fall in the bottom equation. So if I plug in negative 3 here, hey, isn't the negative there waiting for me already? That's why it becomes a positive 3. Now, these can be shifted. If I write f of x is equal to absolute value of x plus 2. What's the breaking point when this becomes a positive and negative? At what value of x will make this a positive and negative? Well, that number is negative 2. So it turns out our new way of writing this would be, oops, let me get that funny. Two versions. This would be x plus 2 and negative x plus 2. So we're writing the same equation. This is the same as x plus 2 absolute value. Same exact equation, except we're going to give ourselves some conditions. Nothing changes when x is greater than negative 2. Because if I plug in anything greater than negative 2, showing the number line, negative 1, 0, 1, 2, negative 3, negative 4. If I plug in values that are on this side here, do we really even need the absolute value? If I plug in 0, 0 plus 2 is positive 2. No absolute value needed. If I plug in 2, 2 plus 2 is 4. No absolute value needed. So it functions like a regular graph. But when x is less than negative 2, if I plug in negative 3, if I plug in negative 3 here, is that negative 3 plus 2 is negative 1? And negative force that to be a positive 1. So when I plug this negative sign here, that flips all my negative values to become a positive, just like an absolute value. Just like an absolute value. So our last problem here, the tricky part is, which version am I looking at? Am I looking at the regular one or the negative one? The regular one or the negative one? So we have to ask ourselves, which version are we plugging in, the left or the right version? So looking at this value, if I plugged in a negative 3, doesn't a negative become a positive? So that's a positive 3 minus 2. Do I need the negative or not? 3 minus 2, would that be a positive or negative answer? If I plug in the negative 3 here, negative 3, negative, would be a positive 3 minus 2. Oops. That becomes a positive 3 minus 2. That's a positive, right? So do we need the absolute value if x is less than -2? No, because that's going to be a positive. Remember, absolute values make everything positive, and we got a positive answer over here. If the absolute value is needed, if there's a negative answer, and if I plugged in a, what we said, a positive, sorry, if I plugged in on the right here, let's plug in -1. -1 is on the right side. So if I plug in -1, negative, -2. This would be negative, positive 1 minus 2 is a -1. Do I need a negative sign for this absolute value? Wait, sorry, let me rephrase that. If I took the absolute value of -1, wouldn't that force it to be positive? So we stick our own negative there to make it positive. So this will be on the right side, and this will be on the left side. So the thing about absolute values is that you cannot get rid of an absolute value just by erasing it. You have to write two different versions, and that's a big deal in calculus. Whenever you have absolute value, you're going to break it up in two different versions. Like what we wrote here. We wrote two different equations right here. Two different equations representing the same absolute value. Two different versions. Now, looking here, we wrote two different versions. A left version and a right version. How did I know the right version needed a negative? Is because when I started plugging in values, all the values on the right turned out to be negative on the denominator. So I needed another extra negative sign to force those to be positive in lieu of writing absolute value sign. So since we made the decision that this is my left and my right side of the equation, we're just going to plug in -2 now. Oh, sorry, we said when if we plugged in -2, this would have been 0 over 0. So we had a trick from before. We're going to go ahead and factor that. Factor on -4 over -1 x plus 2. If you look here, we can divide those out. And our answer is -4 over -1, which is just 4. Turns out that is our limit from the left side. On the right side, though, it would actually give us a whole different answer. If I go ahead and try on the right side, doing the same thing, -4 x plus 2 over, that negative goes away, so just x plus 2. Those also divide out. And the right limit would look like -4. So without graphing it, we can see that the left side would have been 4, and the right side would have been -4. Now let's go ahead and look at the graph. If I go to Desmos, see what's going on here. Oh, yeah. So the equation was -4x minus 8. -4x minus 8 divided by negative value negative x. Okay, so if you go and look at this graph here, we see that, make this change the settings, change the color. Okay. So if we look at this problem, an absolute value in this case gives us two possible answers, the left side and the right side. The left side and the right side. We look at the left side and the right side. Does the left side and right side agree? No. One says +4 and one says -4. As we talked about before, the graph on the left side looks like a +4. The graph on the right side looks like a -4. Now again, how do we do that? When you have an absolute value equation, you want to separate it into two possibilities. A -4x minus 8, that part doesn't change. And the -x minus 2, That's one version. And our next version is negative 4x minus 8 over negative x minus 2. And since it's absolute value, we might need a negative. Now, how do I know which equation goes where? You just go ahead and plug in a value to check. If I plug in 5, 6, 7, 8, see how these are all positive numbers on the right side? If I plug these numbers in, the bottom would be negative. Well, if they're negative, I need another negative to make that positive, because absolute values make all answers positive. So actually, these guys have to go down here. That's the right side. On top, if I plugged in a number that was on the left side of negative 2, negative 3, negative 4, negative 5. If I plug these numbers in, don't these all become positive? Negative, negative become a positive? Let's take 5. Negative 5 times negative is a positive 5. 5 minus 3. No, 5 minus 2 is 3. I don't need an absolute value for that. So it turns out all my left numbers are exactly this copied version. No negative needed. So absolute values always give you two versions, a regular one and a negative one. Regular one, negative one. So how am I supposed to do these problems quickly? Like, how am I supposed to do this? First, you go ahead and look at the problem and you say, let's go look at the next problem. This problem looks just as crappy. I could graph this. I could plug this into a graphing calculator. I could plug this into Desmos. Sure, but our goal is to know how to graph these without. So here's the trick. First thing you should always do, plug in the limit to see what that looks like. So I plug in negative 2, negative 2, negative 2 becomes a positive 2, minus 2, that's a 0, crap. And if I plug in negative, negative 2, that becomes a positive 2 minus 2, that's a 0 also. 0 over 0, we said, is indeterminate. We're going to write our two different versions now because I can't factor with that absolute value sign there. Let's write our two versions. We have a 4, parentheses, negative x minus 2. That's my positive version. And our 4 negative, let me draw that a little better. I'll stick a negative 4 in front. Negative 4, negative x minus 2 over negative x minus 2. Okay? Now, which one's to right, which one's left? Drawing a number line real quick, if I say this negative 2, what are the numbers on the right? What are the numbers on the left? If I plug in 0, 1, and 2, plug it in, check it out. If I plug in 0, 1, and 2, 0, 1, and 2, would these be more positive or more negative? If I plug in 1, 2, 3, 1, 2, 3, this would become negative, right? And don't absolute values have to be positive? So we need that negative sign. So this equation is my right equation. If I plug on the left, negative 3, negative 4, negative 5, into this version on my left, hey, doesn't the negative and negative become positive? Turns out that's going to stay positive. So we don't need an extra negative sign to force it to be positive. So since we have our two versions, we can simplify. If you look at it, we can simplify those. Whoops. You see we can divide this. Now, since we don't have an absolute value signs, we could divide those. We could divide these. So the equation on my left is just going to be 4 over negative 1. Oh, sorry, 4 over 1. 4 over 1. And that is my left limit as we approach negative 2. On the right side, they divide out. Being a negative here, that's going to be negative 4. So on the right side, the graph will look like negative 4 from the right. I want to pause here. Your homework continues with, look at the notation here. This is a left limit, right? Up here, this is a left limit. Maybe we have a right limit on your homework. But look here, there is no notation on the side. So the homework goes from a one-sided limit to a limit at a point, which means both sides. Do both sides agree? The left and the right. Now, if you look at the way I'm writing this, this is a composite function of two different functions. And we're looking at, this is my left side because x is less than negative 3, that's my left side. And that's going to be my right side, which is greater than negative 3. So we're just going to go ahead and plug it in. Please plug in -3 into the problem and -3 here. So on the left side, -3 squared is 9, so -9. Negative and negative is a positive 18 minus 9. That's going to be 0. So the right side looks like 0. The left side looks like, hey, that's a constant. So our constant is -1. Does the left side and the right side look alike? Just like my story about the monks. Does the left side and the right side, do they agree? Can you tell me what the limit looks like? The left side being -1 and the right side being, left side being 0 and the right side being 1. Answer is no, you can't tell me anything about what this looks like. So this is no limit. Because the left answer and the right answer do not agree at the value -3. If you're meeting someone up for a date and you call them on their cell phone because you're there and say, oh yeah, I'm next to the big tree. And they're like, well, I'm next to the small tree. Are you guys in the same spot? Nope. This next problem here is called, I just forgot what it's called. A floor, the floor and the ceiling. When these problems, what happens is we do not use any decimals. It's all whole numbers. So if I plug in numbers like 0 and 1 and 2, let's talk about plugging numbers 0, 1, and 2. If I plug in 0 into this graph, 0 minus 1 is -1. Okay. What about if I plugged in 0.5? 0.5, 0.5, 0.5 minus 1 is -0.5. But we can't use that number. We use the lower floor. We go down. What's the whole number on the bottom? Well, if we start at -1, we haven't gotten up to the next value yet. So it turns out this is what the graph looks like. It looks like a line with a hole at the end of it. And I'll explain why do we look at it this way. At 1, if I plug in 1, my next step, 1 minus 1 is 0. That is a whole number. So we can graph that. What about if I put 1.5? 1.5. If I plug in 1.5 in there, 1.5 minus 1 is 0.5. Well, that's not the next whole number, so we actually have to go down to the floor. We're back at 0. We're still at 0. We're at 0 at all the decimals to my next whole number, 2. At 2, when I plug in 2, 2 minus 1 is 1. The idea is we only graph whole numbers. Now, why is this beneficial? Does this really happen in the real world? Well, yeah. Imagine if your mom asks you to buy 2.5 apples at the supermarket, right? Let's say there's 5 of you guys. Each of you guys get half an apple. Can you buy 2.5 apples? No, you would have to buy 3. And that's called a ceiling. You round up to the nearest whole number. And that is demonstrated by this notation. If I wrote this is the floor. This is a ceiling notation. If you ever see something like this, it means round up to the next whole number. So this is the floor, and this is the ceiling. When it comes to populations, you've seen people say like the US, the average number of kids is like 2.3. Can you really have 2.3? What family has 2.3 kids? Okay, you can say, oh, my wife's pregnant, right? Well, no, you only have how many kids? 2. Third one's a fetus. I'm just kidding. Well, however you want to count it, but we can say you have 2 kids. So that's a floor. If you go to the market, and let's say you're buying candy. Candy is 50 cents each, okay? And you have $3 and $3.25. Okay, $3.25. How many bars of candy can you buy? Can you buy 7.5? No. If each bar of candy costs 50 cents, you can only buy 6 bars of candy. So we have to go down. That's the floor. You can't buy a half bar. You can't break it in half at Vons and say, hey, I just want half of it. I have 25 cents for the other half. So it's important for us to have these types of methods to round up and round down called the floor and the ceiling. If you look here, the graph itself starts at -1, and I'm at -1 till I hit the next whole number, 1. That gave me 0, like we graphed. It stays 0 all the way to 2, which gives me finally the next step, 1. And these are what we call step functions. Awesome. You guys might have seen them in Algebra 2. So the question here is, what is the limit at +1? What is the limit at +1? So let's look at the graph and look at +1. Here's the graph. +1 is right here. What is the limit as we approach 1 from not only the right side, but also the left side? Does the right side and the left side agree with each other? The right side says, hey, as I approach 1, that looks like 0. The left side, as we approach 1, it looks like -1. Does 1 and -1 agree? Turns out they do not. This is no limit. So on your homework, it turns out all the answers between 4, 5, 6, and 7, if you're listening, are going to be actually no limit. Then the answer is no limit. It does not exist. And I want you guys to make sure you guys can do that. The last part of your homework is really just, come on, go. It's just a multiple variety of possibilities. You have absolute value, you have piecewise functions, right? And you're going to tell me what those limits are. Do they even exist? Let's just do one of these values. Let's do number 9, and we'll call it a day. Guess I've been very patient. If I plug in -3, hey, -3 from the left side and the right side, let's plug in -3. Plug in -3, -3. And if I plug in -3, that's going to be -9 plus 24 minus 16. This gives me 24 minus 25, which is -1. The right side says -1. The left side says -4. Does the left and right side agree? Nope. Then no limit. Or does not exist. But let's look at the number 10. Oh wait, no, let's look at let's look at this one here. Okay. Is this automatically going to be does not exist? Well, what does, if let's plug in 1. Let's plug in 1. That's 1 minus 1 is 0. 1 plus 0 is 1. I'm done. The reason why we had problems on the last problems with absolute values is that they were dividing. It was like a absolute value divided by something. And it became 0 over 0. And then we had to do this funny separation. But for the most part, absolute values just look like what they are, absolute values. Plug it in. Well, that's what it looks like. If we want to verify that, if we write two versions, x plus x minus 1, okay, and x plus, well, let's do minus x minus 1. Okay, these are my two versions. Which one is which? If I plug in big numbers, here is our chart. Here is 1, 2, 3, and 4, 0, -1, -2. If I plug in 2, 3, and 4, would this stay positive or negative? This would stay positive. So this is my right side. Plugging -2, -1, -3, this would become negative. So we need a negative to make that back into a positive. This is our left side. Well, let's plug in 1 to see what happens there. If I plug in 1 here, 1 minus 1 is 0. So it's 1 plus 0 is 1. That's the right side. If I plug in 1 here, because remember we're trying 1. Be 1 minus, well, 1 plus 1, so 1 minus 1 is also 0. Does the left and the right side look the same? It does. And it's our limit. It is equal to 1.